All right. 1.2, properties of limits. This section is going to be essentially, we're going to be using it the rest of the time we're working with limits. But this section also kind of presents itself nicely for use when you don't really have the equation of the function, but more you have just like a graph of the function. You don't have its equation, or you're just given some limited pieces of the function. Okay, so let's go ahead and look at it. I'm trying to put all the important theorems and stuff in green, and then the mathematical content in blue, but we'll see how that works out. Properties of limits. If the limit as x goes to c exists, and the limit as x goes to c of g also exists too as well, additionally, okay? So what that means is we know that two functions, f and g, at the same value of x, call it c, their limit exists. Does that mean they're continuous at c? Not necessarily. They easily could be, but we do know that the limits exist. Where k is subconstant, then the following are true. We have what's called the addition and subtraction rule. And it basically says the limit of the sum is the sum of the limits, okay? So this is a pretty helpful rule. It almost feels like the distributive property. You could treat it as the divide and conquer property. In other words, if you're trying to find the limit of a function that has multiple terms that are added or subtracted, any number of terms, doesn't have to be two, you can find the limit of each piece separately and then combine your results with the indicated operation, add or subtract. Number two, you'll hear me say this quite a bit throughout the year. A constant multiple goes along for the ride. He's there in the beginning, he'll be there at the end. So if you're taking the general limit or any limit of some constant k times a function, pull the constant out front. Take the limit of the function itself, and then you can multiply the result by k. Number three, multiplication, okay? It feels like the distributive property, which we're never allowed to do for multiplication. If you have the limit of a product, it's the product of the limits. Wow. The limit of the first times the limit of the second. And it also works for division, which is number four, provided that you're not dividing by zero, right? So, and let's do this last one, number five, the limit of exponentiation. If you have the limit of a function raised to a power, bring the limit inside. Take the limit of the function first and take the result and raise it to a power. So 1 through 5 are pretty straightforward. Essentially, anytime you have a variable, whether they're multiplied or divided, added, subtracted, exponentiated, you could take the limit of the individual pieces, get the result, and then combine the results using the indicated operation, okay? So how do you eat an elephant? Not one big bite. You eat it one little bite at a time, okay? One little bite with barbecue sauce, if you so choose. Now, number 6 is a little bit different. It's composition, all right? So let's say that we actually know not only that the limit of g exists at c, but let's say we know it to be this value L. Then the limit as x goes to c of f of g, composition, is the limit as x goes to L of f. If you remember composition of functions, it's kind of like a sequence of events, right? You start with this input, you apply it to the inside function, and that input, boom, gives you an output. That result then you use as an input on the next function, and then you get another output, right? If you look at just the composition without the limit, you start with x, you plug it into g, and you get g of x. That result, g of x, which was a y value, now becomes an x value as you plug it into the next function f. Inputs become outputs, right? It's a sequence of events. So if you think about the limit, you could bring it inside. It's the limit as x goes to c of g. Well, what is that equal to? It's L. So now instead of calling it f of L, we're taking the limit as x goes to L of f. So it's still inputs become outputs. Those outputs become inputs. We just keep it in the context of a limit. So, and I'll show you an example here so it'll make more sense. But if you want to put an intermediate step here, let's call this f of the limit as x goes to c of g of x, okay? It's the same idea that we've been doing up above. We could bring the limit right up there next to the actual variable piece. Now, of course, what is this equal to? Right here? It's equal to L. But the danger is we don't want to just do a substitution and say it's f of L, because that's taking the context of a limit and putting it now into a function value context. L will be our new input now, but it's not the input that we're going to go try to stand at. It's the new input that we're going to be approaching, okay? Inputs become outputs. Those outputs are now our new inputs. We just keep it in the context of a limit, okay? All right. The other thing that's going to come up here when we do composition especially is this idea. And just a reminder, the limit as x goes to c of some function, I'm going to use h of x here so you don't think it's any of these. It exists if and only if the limit as x goes to c from the left of h of x equals the limit as x goes to c from the right of h of x. This is going to be important, especially because you're going to get like these pieces where it appears that the limit of one part doesn't exist. But if you look at them separately from the left and right, all the way through, especially on the composition, you can actually have the actual limit of the whole thing existing, even though one of the limits doesn't exist. I'll show you what that means. Okay, this is something new that I'm emphasizing this year. But here's kind of the general spirit of the properties of limits. Look at the left side. If you're taking the limit as x goes to c of that big old thing, it's pretty intimidating looking. You have 1, 2, 3, 4 different places where there's variables. The x, the f of x, the x, and the g of x. All you got to do is reproduce the limit and put it, boom, right in front of either the variable x, in this case, which we could evaluate by direct substitution, or the functions f of x and g of x, which we're going to be able to evaluate from either a graph or given information. Okay? Divide and conquer. That's kind of the best way to think about it. Divide and conquer. You just got to put it all back together again, right? Divide, conquer, and then reassemble. I don't know if you want to do that. All right, we just conquered you as a people. All right, let's get everybody back together now. Note, okay, so it's in red. These functions need not be continuous. We also talked about that. So be careful concluding something such as the general limit is equal to f of c, or that just because one of the limits is d at e, that the entire limit is also. That's the composition one. When a function is not continuous, the limit of the composite function still may exist. It just has to be examined from both sides carefully. And this is really important because this is kind of what's new that I'm emphasizing this year. What starts as a two-sided limit may in fact become a one-sided limit. So if you want to come back up here on number 6 and put like a couple of stars by it, that's the one that could be tricky. Not tricky, but it requires more thought. And in the past, that's kind of slid under the radar. All right. I have some examples in here that are new this year. So Landon, you'll get a taste of what I mean. All right. So let's just kind of dip our toe into that water and see how this works. All right. We've got example 1. Given that the general limit as x approaches 3 of some function f of x is 8. All right. And then for some other function g of x, as we approach 3 from both sides, we're approaching -2. And a third function, wow, h of x, as we approach the same x value of 3, we're approaching 0. These functions may or may not be continuous, but all we know is that for each of these 3 functions at 3, at least the roads are lining up at 8, -2, and 0. Look at the types of questions we can then answer. What would be the general limit as x goes to 3 of twice f of x minus 4g of x? Well, using the properties of functions, if I can somehow get the limit to be right there in front of f of x and g of x, I can use direct substitution. So how am I going to do that? I'm going to rewrite it, okay? So let's go ahead and put the limit. Again, you can replicate it as many times as you need, and we'll put it right in front of those two highlighted pieces. So this becomes 2 times the limit as x goes to 3 of f of x, minus 4 times the limit as x goes to 3 of g of x. Now, if you want to know what properties we're using property 1 and property 2. Property 1 is the difference property, and then by bringing the 4 and the 2 out front, we're using the constant property. It's kind of intuitive, though, hopefully. And now, since I've got it down to these things, now I can use direct substitution. All right, what is the limit as x goes to 3 of f? Well, it's 8. So this becomes 2 times 8 minus, what's the limit as x goes to 3 of g? It's negative 2. And that's it. Free response, you can stop. If we simplify, though, we get 16 plus 8, which is 24. So it feels a lot like just function substitution, right? Like if I told you f of 3 is 8 and g of 3 is negative 2, what's twice f of 3 minus 4g of 3? It has that same feel. It's just in the context of a limit. Okay? Make sense? All right. Go ahead and try B on your own. And go ahead and take the time to do that substitution step with the properties. In the past, I've almost encouraged students to skip it and just go straight to direct sub, but that could be a little dangerous. A little too footloose and fancy free. Yeah. If you're done, you want to look up and see if I'm right? You can do that. If you got the same answer I did, that's good. I feel better about myself. Go ahead and try part C then on your own. And I'll work it quietly up here by myself too. Yeah, you can stop at free response. Oh, yeah. Right. Yeah.
I just like break these two out into two separate things if it was
Wait, let me see.
like if they were just the same thing.
Oh, well, you're still missing the g of x, but you could do it. Instead of squaring them, you can multiply them. But yeah, you'd still need g of x in there. Yep, that'll work. And hopefully you get the same answer we do. Yeah, good.
Is g of x the same thing as the limit of g of x?
No. No, g of x is some unknown function. All we know is the general limit is negative 2. We don't even know what g of 3 is. It could be negative 2. It could be undefined. Yeah. It feels a lot just like substitution, though, of function values. It's just substituting limit values. And it's because all three of these limits exist that it feels almost too easy. Like there should be something more difficult to it.
So whenever you do have like the f of x, you would sub in the limit.
Right, right, right. Again, as you're plugging in, make sure like your denominators cover everything they're supposed to. Make sure your radicals cover everything they're supposed to. You know, you might have to come back and extend something or erase it. Yes.
You did X approaching C.
Oh, yep, yep. Monday. Mhm. Yeah. Well, you got 10 in the bottom there. You have x plus 7. Remember, if you're not writing the limit anymore, you got to have numbers there. So if you're on part C, I've stopped right here on the bottom right. I put the limit as x goes to 3, but I put x plus 7 in parentheses. You could put just x in parentheses and then think of the plus 7 as an afterthought. But how do I evaluate the limit as x goes to 3 of x plus 7 if I'm not given any information about x plus 7 up here? Direct substitution. Yeah, very good. If you have powers of x, it's kind of like defining its own function. Direct substitution, 3 plus 7 is 10. It's only when you have the unknowns that you got to resort back to those 3 pieces that you were given. So this could be a good place to stop on a free response because it's defined. It ends up being the whole second term, right, is 0 over 13, which is 0. Cube root of 8 is 2. 2 divided by negative 2. So negative 1 will be the multiple choice. I put 3 plus 10. I'm really having some difficulty with that one. You did. 3. No, but it does matter. If this were a free response, it would matter. I would not get it right. If it were a multiple choice, I would have gotten lucky and gotten the right answer nonetheless. I don't really like to rely on luck. I like to rely on my wife telling me what to do. That has worked out well so many times. But she's not here, so what do I do? Y'all help me out, right? In her absence. Okay? So again, this one's pretty straightforward. You have 3 functions. All of them are defined at that point, all right? The limits are defined, I should say. Okay, now example 2, we're not going to get too much into it before lunch, but notice it's a little bit different for a couple of reasons. We have graphs of f and g now, and I did hand draw these. And notice there are discontinuities all over the place. So this is where it gets interesting. If you get an answer of D and E, you have to break it up and analyze it from the left and right. That's what one of those red notes up above said. If at any point you get an answer of D and E for the general limit, you got to break it up into left side and right side, okay? And I haven't been emphasizing that in the past because it hasn't really shown up on College Board tests, but every year they try to, you know, accentuate something, which is good. They do something like several years ago was the IVT that teachers were addressing, but not really getting into much detail about. And you'll see later in the year, it scored a 0.98 out of 9 points, the lowest free response ever. And so now every teacher teaches the IVT pretty darn well. All right. So anyway, I'll stop right here. Y'all can go to lunch. We'll pick up with example 2 when y'all get back. Have a great lunch.